Every day, people around the world who suffer from severe paralysis struggle to communicate and interact with others because they can't move, type, or speak. Brain computer interfaces, or BCIs for short, have the potential to restore autonomy to these people by translating brain activity directly into intended messages, bypassing their paralysis entirely. In previous work, we demonstrated that a clinical trial participant who lost the ability to speak due to paralysis could indeed control a BCI to generate full sentences by simply trying to say the desired words. However, this initial proof of concept was limited to a small vocabulary. In this work, we designed a spelling BCI with the same participant that allowed him to silently spell out sentences from a much larger vocabulary. Here, you can see him controlling the BCI to respond to a question in his own words. In this approach, the participant activates the BCI by simply attempting to silently speak. Then, he silently attempts to say code words that represent each letter in his intended message in order. Afterwards, he attempts to squeeze his hand to indicate that he is done spelling. Throughout this process, our BCI used custom deep learning algorithms and advanced natural language models to translate his brain activity directly into text. Our BCI succeeded in decoding the participant's intended sentences in real time with 94% character accuracy at around 7 words per minute. Importantly, it enabled him to communicate with a vocabulary of over 1,000 words, and offline simulations illustrate that the approach can feasibly generalize to over 9,000 words. These demonstrations represent an important milestone for communication BCIs controlled by natural attempts to speak, bringing the technology closer to clinical solutions for many people who have lost the ability to speak on their own.